representations have similar vectors. So imagine that we have vectors only with 3 components. So you could see this is like width, length, and height. So you have things in space. So if you put them in a cube, maybe the word laptop and the word computer will be somewhere in the same area of space, or Spain, Italy, Europe, and France would be somewhere here, and maybe car would be far from lorry, but not so far from lorry and motorbikes. And okay, so you have these relationships. So the vectors, which are like coordinates in a high-dimensional space, represent the words. So back to the, so this would be a very small neural network. You have three inputs, so the small black dots are like input data. And then this input flows to the hidden layer, which has 3 neurons. They get excited or depressed, and then they communicate this to the output layer, which has 2 neurons, and they get excited or depressed. And then the output is maybe what you want. So here you would have 2 output units. You could interpret, I don't know, maybe it's two qualities of your data or something. Usually you don't use 2 and 3, you use hundreds, and you use many layers in the system. So the canonical architecture, not the only one, the canonical architecture, the canonical design of a neural network-based machine translation system is called the encoder-decoder. So the idea is very similar to that of building a representation for the source sentence, that would be encoding, and then building a target sentence from the representation of the source sentence, which is called decoding. So this is the canonical architecture. So the encoder, what it does, it reads one by one representation of source words, or could be not words, but also units smaller than words, and builds a representation of the sentence. And then, out of this representation, the decoder predicts one by one the target words. That's, you would call this the canonical architecture. So I don't know if you can see this. Imagine that you are encoding the sentence, my flight is delayed. So you start with a representation of its words. So you have some vectors that represent the words that you have learned somewhere. For example, the first, you can see the first encoder there, the first step. The encoder is fed a representation of the empty sentence because it hasn't started, and then the word my. And it generates a representation of just a sentence that starts my. Then you feed the same encoder, you feed the word flight. So starting with my and the word flight, you get a representation for my flight. And then my flight is delayed, my flight is delayed. So you end up, and then full stop, you end up with a representation of my flight is delayed, which is a vector. Yeah? It's a group of units of your neural net have particular activation values. So this would be the encoding of a sentence. And then you translate by decoding out of it. So you start with my flight is delayed. You send it the start symbol. You say, hey, you have to start translating. And then the decoder gives you probabilities for words. It tells you the probability of, so the translation should be mi vuelo está retrasado in Spanish. So it gives you the probabilities of words, like many words, and the probability of me happens to be the highest. So you say, oh, this is going to be my translation. So you basically say the first word of my output is going to be me, which is right in this case. And then you feed this into the decoder, but you start with a new representation that you built where you have subtracted the first word. So you do this by separately, so now you have the decoder, you read you have the next word is predicted to be vuelo, which is the most probable because it has probability 31%. And then you generate the representation that you say, okay, this is the representation I obtained by translating my flight is delayed and having already subtracted from it the word me. And you go on and you go on and you go on until you get, hopefully, you get an end of sentence symbol. And it's very probable, so then you cut. Excuse me. So if the system predicts an end of sentence symbol, then you have a translation. This would be a very simplified way of doing this. So it's like You could say like you're basically sticking words into a representation like this, and then you pull translations out of it. So there is no way to know which word came from which word, because you work with representations of the whole sentence. So the idea that we had in statistical machine translation, you probably remember, where you knew where things came from, it's gone. You don't know where the words come from. You just know that the words are predicted from the representation of the source sentence. So this is a new technology, completely new, and this means that there's a new kind of output, which means that translators have to think differently now. So first thing is that neural machine translation requires specialized powerful hardware. So most of the computers we have use CPUs, but they use GPUs, which are the graphics part of the computer. And they found out they're very good at doing some of the maths that you do with neural nets. So now what people do is they buy computers with huge graphical processing units, which take care of all the mathematics of neural nets. As I said, it works with representations of the whole sentence. It's hard to know the source for each word. It produces grammatically fluent texts usually. It's very good, very, very fluent. And it also produces semantically related or semantically motivated errors. So for example, if a word has not been seen during training, it is replaced. So you can replace palace by castle. Not bad, but not what you want. So you get, here's a door to terminological trouble, okay? Or you can get a paraphrase, like you input Michael Jordan and you get the Chicago Bulls shooting guard, which is right, but it's not probably the right translation in context. Or sometimes you get the wrong country, like you input Tunisia and you get Norway. When you work with small units, like subword units, the system may invent new words like engineerage or recruitation, just by putting together pieces of words. This is good because in a language like Turkish, you have to put together a lot of things to make a word because you have an agglutinative language. But then you can put them in a creative way and create new things that are not legal. So post-editors, that is, most of you, have to pay very special attention, and as Alex said before, the cognitive load changes. It's harder now because you're looking for not obvious errors, but very subtle errors. So what's the traditional way of doing things? That's post-editing. Most of the people think, okay, I run the machine translation through my text, I look at the machine translated text, and I post-edit it. Usually a post-editor, professional translator would edit raw empty to produce a translation that is adequate for the intended purpose. If raw empty is close, then post-editing may be feasible. If it isn't close, post-editing is unfeasible, and many translators just go and say, nah, I'm going to translate from scratch. How close? Well, it depends. 10%, 20%. Depends on the language pair, and on the post-editors. Some post-editors are better users of machine translation. They make make more out of machine translation. Some others just look at machine translation and say, oh no, I cannot do anything with this, and they translate from scratch. So you have you have people in the system. As computer people say, problem exists between keyboard and chair. Okay? So we have a human, a professional, and they're all different. So this is interesting for quality estimation, because quality is not the same for everyone. So post-editing is an additional skill set. It's something that one has to learn. You learn to translate, you learn to post-edit. You need to be familiar with what the machine translation system produces, be good at editing, moving words and phrases around, using macros, paying attention to the source text, so keeping an eye always on the source text so that you don't get fooled by a very fluent translation. One thing that is related to what Alex just said is that machine translation looks bad because it's always shown. When you use translation memories, the system decides not to show you fuzzy matches that are less than let's say 70%. So you only see rather good stuff, because the rest is just not shown. In machine translation, usually it looks bad, because everywhere, machine translation always produces output. And then we need to estimate its quality so that when we know it's going to be crap, you don't show it to the translator. You just let them do it the old way. Problem with machine translation is that it's available, so it's you see everything when it's good and when it's bad. I stole this idea from Morkens and Way there. They started to run around this idea. Post-editing, translators don't like post-editing. They're angry. They have to fix the same mess that the machine has done. They have to fix output, which is always the same mistake. And they feel, what do I do with this? I don't know what to do with this. So some experts, like Josetje, who is a translator, contend that translator would feel better if, and be more productive if machine translation was used in different ways. For example, but before, one important thing is that translation professionals may be wrong sometimes about how useful machine translation is. This is a study by Plitt and Masselot at Autodesk, which is a big graphics company. And they translated with a well-tuned machine translation system. And it's funny that every translator was saving time. They were all saving time. So the productivity, the green bar, was their productivity when using machine translation and post-editing. But you ask them, you say, what do you feel you were more productive with machine translation or translating from scratch? And you get all kinds of opinions. Some people say, no, I will never post-edit. I am faster. No. Some people say, oh, I am post-editing. Well, they were right. Some people say, nah, no, you were better with machine translation. So this was this case. In other cases, it could be the other way around. But the lesson is, perception of productivity is not the same as productivity. So measure yourselves. That's whenever you're going to adopt a technology, measure yourselves, or have yourself measured, or have someone measure the productivity. New users. So we have the machine translation, and what else is there out there in addition to post-editing? So I'll cover three modalities very fast because I think I'm running out of time. One is interactive predictive machine translation. The other one would be the marking of target word confidence in proposals coming from the translation memory. And the other one is fuzzy match repair. So repairing proposals from the translation memory. Very important. There are no conclusive productivity studies on these yet. So they may feel very good, but maybe good old post-editing is more productive. Sorry, translators, I know it's boring, but sometimes we have to measure. So interactive or predictive machine translation, it's a very old idea. As you, the professionals, type the translation, the system proposes continuations, completions of what you type. So it tries to predict what you're going to type, a bit like your mobile phone. You're writing a WhatsApp, and it goes like, it predicts a word so you can type less. So this is the idea, but instead of predicting a word in general, it predicts a word for that translation. So you select one and go on typing. This is all, it's been around for a long time. Transtype, Transtype 2, and then you have things like LILT or Kytra, all use statistical or neural MT. Neural MT uses predictive decoding. If you remember how a neural system just predicts the next word, just perfect for this, because it tells you what the next word is. But could use anything like rule-based MT. In fact, a recent thesis in my group was about using black box MT, any MT in predictive encoding. This is commercially available in many products. I'm sure it's also in Memsource, auto-suggest, auto-complete, auto-write, all of these things. So you start typing, you have the English sentence. This bill is very similar to its companion bill, which we dealt with yesterday, and you're translating into French, and you start typing a C, and then you don't get anything, you type an E, and then you get projet de loi for bill. And then you accept, and then you type an E and you get E, you get EST, which is right, and you type T and you get vraisemblable, which is very similar, and you go on and go on and go on, and the system basically saves you typing. Okay, sorry. Okay. So that's a very natural way of translating, but it has high cognitive load, as you know when you use a mobile phone, because sometimes it predicts things, you have to check the prediction. So, different stuff. Another way, edit hints. Imagine, okay, so this is the typical situation in CAT. You're translating this is English to Catalan, the example, I think it's pretty transparent. So when you're using a CAT system and you bring a proposal from the translation memory for a new segment, the system is nice, it highlights the source words that don't match. So for example, I want to translate connect the printer to the computer. And I get from the translation memory, connect the scanner to the computer, which has the Catalan translation, conecteu l'escàner al ordinador. Catalan uses the Frenchy word for computer, ordinador, okay? So, that's nice, but it would be much nicer if it told us what to change in the target, okay? So, it tells you what changed in the source, and then you are the translator, you know what to change in the target. But it would be nice if it told you, no, you have to change this. I suppose this is the word you have to change. So you can do this. And you can use machine translation to do this. So, how do you do this? First, you determine the words that changed, usual, in the source. Then you machine translate segments, small portions of the segment around the mismatches. And then you try to mark the words where the machine translated target segments match the target side proposal. I'll show you an example now. So you basically put together a bit of context around your problem word. You translate that with your machine translation. You try to find it in your target proposal, and if you find it, then you can know what changed. So for example,